Here we go, part 2, antiderivatives and trigonometric functions. So we're given that the derivative of some function f is 2 minus 3 sine x. We want to find f of x such that f of 0 is negative 2. Okay, fair enough. I can do this. F of x is going to be integral 2 minus 3 sine x dx, right? No big deal. Yeah? Cool. So this is 2x plus 3 cosine x plus c, and we're done, right? Well, no. Because we're also given that guy right there. We're told that at x equals 0, the function is equal to 2. That is telling me that I'm going to find c. So what we're going to do, negative 2 equals 2 times 0 plus 3 cosine of 0 plus c. We solve for c. We are going to get negative 2 equals 1 plus c. c is negative 3. Therefore, our specific function f of x, no longer having a constant of integration, is 2x plus 3 cosine x minus 3. And there we go. Nothing too terrible. I think we can do this all day long. And I hope you agree with me that we can do this all day long because we have a similar problem here. This time we're given the second derivative of g, and we're told that the first derivative evaluated at 0 is 2, and the function evaluated at 0 is 3. Find g of x. Well, if we integrate the second derivative, what's that find us? Well, that finds us the derivative of g. Okay, cool. I can do that. I hope you can too. And on that note, pause the video and give this a go. We're going to get sine x minus e to the x plus c. And here we're given this initial condition on the derivative, so we can actually find c. We can say 2 equals sine 0 minus e to the 0 plus c. We solve for c. We get that c is equal to 3. So g prime of x is equal to sine x minus e to the x plus 3. Cool. But I don't want the derivative of g. What I really want, what would be great, is if I knew what g of x was. That's what they're asking me for right here. So what do? Well, to find g of x, we're going to integrate the derivative. Sine x minus e to the x plus 3 dx. Let's go. G of x is equal to negative cosine x minus e to the x plus 3x plus some constant of integration. I'll use a different letter, call it d. And again, they give us an initial condition for g. They tell us that when x is 0, g of x is 3. So 3 equals negative cosine 0 minus e to the 0 plus 3 times 0 plus d. Solving for d, we get that d is equal to 5. So what does that mean? Well, that means that g of x, in all of its wonderful glory, is equal to negative cosine x minus e to the x plus 3x plus 5. These initial conditions allow us, or any ordered pair they give us, allow us to find the specific constant of integration for that problem. Now, as long as we're talking antiderivatives, integration, let's do some definite integrals. Wouldn't that be fun? Heck, yes, you're saying. Can't wait. So, integral from 0 to pi over 2, e to the 2x plus cosine 3x dx. So, depending on how comfortable you are, you might want to split this, and I'm going to leave the constant of integration off for now. but you might want to split this into two separate integrals. And you should be comfortable with u substitutions. Each of these require their own little substitution, but what we end up with is 1/2 e to the 2x plus 1/3 sine 3x. And these are the antiderivatives, and we don't use a constant of integration because we have limits of integration. We have 0 and pi over 2. And do we remember what to do with this? That's the big question. I hope so. We substitute the top one, and then we substitute the bottom one, and we subtract. So this becomes 1/2 e to the pi plus 1/3 sine 3 pi over 2 minus 1/2 e to the 0 plus 1/3 sine of 0. And now we crunch numbers. We've got 1/2 e to the pi minus 1/3, because sine 3 pi over 2 is -1. And then we're subtracting 1/2. So this definite integral is exactly equal to 1/2 e to the pi minus 5/6. There we be. So one last example to do. It's going to be another definite integral. So here we go. I hope you're ready for this. This looks terrifying. Well, actually not really. It's not that bad. So antiderivative of the first term, that's just x minus, alright, this one looks kind of hairy, so I'm going to do it separately. We've got 1/5 integral secant squared x over 10 dx. Ew, yuck. I mean, I'm scared. But, you know, I remember we can use a u substitution. U is x over 10. du 1/10 dx. So multiply by 1/10, multiply by 10 to balance things, and what do we have? Well, we've got that x minus 1/5 times 10 is 2. Integral secant squared u du. Now that I can take the antiderivative of. Antiderivative of secant squared is tangent. So I've got x minus 2 tangent x over 10 was what u was. And we're evaluating this from -5 pi over 2 to 5 pi over 2. That really wasn't as bad as I thought it would be. I hope you're feeling the same way with me. Now we do our substitutions. So we have 5 pi over 2 minus 2 tangent. Well, 5 pi over 2 divided by 10 is pi over 4. Minus -5 pi over 2 minus 2 tangent -pi over 4. And evaluating this, we end up with 5 pi over 4. Sorry, I lie. We end up with 5 pi minus 4. I got my numbers combined up there. So there we go. Really nothing new. Just taking these old ideas from all the other antiderivatives that we took in the definite integrals and indefinite integrals, and now we're just tossing trig functions in there to make life a little bit more exciting.